Many real-world systems involve distributed loads, that is, loads that don't look like a single force acting at a single point. One of the most common distributed loads is weight. If we think about this brick wall, we can see that the wall could be thought of as a collection of particles. Each one of these bricks, it's a terrible color, each one of these bricks has a position and a weight, right? We could have a weight and it has an XY location. If we found the average location of all the bricks, we would discover the centroid. And if we found the weight of adding up all the bricks, we would find the weight of this section of the wall, which is what the beam below has to hold up. But it turns out any body can be thought of as being composed of an infinite number of little particles, each of differential size, each with their own differential weight. Just think of the body as a collection of molecules and atoms, each with their own weight and location. And when we add up the individual weights, we get the overall weight of the object, and we call the location that acts through the center of gravity. So for an object of uniform density, this is the exact same location as the centroid. So the center of gravity is the same as the centroid for uniform density or homogeneous objects. It's only different from the centroid. Remember, centroids are geometry problems. Center of gravity is a mass thing. The only time they're different is if you had some object that had varying densities in it. So for example, if we had a tank like this, but the tank had a wall in it, and this side of it was filled with sand, and the other side of it was filled with water, those have different densities. And so even though the centroid is still at the geometric center of our system, the center of gravity is probably going to be skewed towards the water here a little bit. I'm making this up as I go. There's math we could do to find out for sure. So what we want to do is we want to find the center of gravity so that we can figure out where to put the weight force that's acting on an object. In general, it'll just be the centroid, and that's all we have to worry about. But I wanted to show you a little bit of cool math to show you why that is. So imagine we start with a rod. So this is a long bar, uniform cross section, and we're going to let it sit on the x-axis, and going up this way is the y-axis. I think you can imagine that we could pick a little differential portion of this bar, and that little differential portion has a weight that we could call dw, the differential amount of weight. Well, we know that the overall weight of the entire bar is what you would get if you added that dw to the one next to it and the one next to it and so on until we'd done all of the differential weights. In other words, we add up all of these dw's and we get the total thing. Anytime you're adding up a bunch of differential things like that, it's code for integral. So we're going to do the integral of dw to find w. We need to get some limits on this, and so let's say that the bar is of length L. Now our limits of integration would be integral from 0 to L. Just like we could do that, we could also think of the fact that each one of these differential weights is going to create a moment about the origin here. All right, so for this distance x, that would be the moment arm that dw acts over. The moment created by dw looks like x times dw. And don't worry about the signs. Technically, this would be negative, right, because it's a clockwise rotation. We don't need to worry about that here. If we wanted to find the total moment, we would just go ahead and add up all of the little x times dw's, one for each of our differential elements. In other words, we would do another integral from 0 to L of x times dw. But here's the thing. The rule for the center of gravity is that the center of gravity is located at a place, let's do a different color here. The center of gravity is located at a place that we're going to call x bar, kind of like the average location, x bar. And what we want is we want the location to be such that when I take the overall weight W that comes from integrating dW, we want that weight to be at an x location that creates the same moment as all the little ones. In other words, x bar times W, that's the moment arm, times W, so that's the moment caused by the weight, has to be equal to all these little ones. The integral from 0 to L of x dw. And so we can solve that for x bar and find that the centroid lives at the location integral 0 to L of x dw divided by the weight. And we can sub in the weight here, which was 0 to L x dw. Oh, look at that, I miswrote. Made a little error here. Come back and erase that. That's x dw, sorry about that. And divide that by w, which we found already to be the integral from 0 to L of just dw. So now the question that might be coming up in your mind is, beyond the fact that there's a bunch of math that just happened, is what is dw? How do we find dw? So let me make a new screen here and I'll show you. dw is the weight of a little thing. Remember, we find weight by multiplying gravity times something. Multiply gravity times the differential mass. Right? So we got a little mass times gravity gives us a little weight. Well, what's mass? Mass could be thought of as density times volume, or in this case, a differential volume, a little v. And I just draw arrows through a line through my v like that to make you see that it's a capital V. You can't really tell the difference between a lower and a capital V otherwise. So that's all that is. It's just a capital V. So if we go back now and just talk about our box again, right? The little element So if we go back and look now just at this little box, the little differential piece of weight from that rod, it has a weight of dw, and we could think of it as a cube. And cubes have side lengths that look like dx, say dy, and dz. And so the volume of this thing, d volume, just looks like dx, dy, dy, dz. All that comes together when we sub in. We can now write that dw, the differential weight of this element, is equal to density times gravity times the side lengths of the box. All right, where's this guy going with this? Well, when I sub this in to our thing that we just came up with for x bar, what we end up with is the integral of x, remember it was the integral of x dw over the integral of dw. We get to replace dw now with something a little more detailed. So it's going to be x g rho dx dy dz divided by the integral of dw, same thing, g rho dx dy dz. And what you might realize is if we have uniform gravity and uniform density, those two bits can be pulled out of the integral. In other words, we get to write g rho, and that'll happen on the bottom too, by the way, here, right? Outside of the integral times the integral of x dx dy dz, and here's the integral of dx, dy, dz. And so, lo and behold, the g rows cancel out, and what you're left with is actually the mathematical definition of the centroid. So that's a really fancy way of saying that for a homogeneous object, the center of gravity is the centroid. For homogeneous object. Thanks for hanging out with me to do a little bit of math on that one. It's kind of fun. So how do you use this? That's the real question, right? How do we do something practical with this? Well, we're going to follow the same problem-solving steps that we always do. We're going to make a free body diagram. We're going to do force and moment balances. We're going to do geometry and algebra. But now what we need to do is we need to come up with the force that belongs on this free body diagram and its location. Well, the way we do that is we treat weight like any other loading function. And so the overall weight is simply the integral of, say, w of x dx, if we're doing the 2D version here. And the location that it acts through is x bar. The really nice thing is this has been done and put in tables for most common shapes that you're ever going to encounter. And so you can simply go to the back of the textbook and grab these properties for whatever shape you're dealing with and drop them right into your solution. And once you have these two pieces of information, you're ready to draw the free body diagram and just add that into all the other force and moment balances that you were going to do anyway before you work on geometry and finally the algebra that it takes to solve the problem completely.